first, let's look at what is meant by log x. A logarithm is actually just another way of writing an exponential function. The logarithmic function with base b, where b is greater than 0 and b is not equal to 1, is denoted by log base b. So notice the notation, log with what looks to be a subscripted b, and is defined by y equals log base b of x if and only if b to the y equals x. So notice we can use this to convert from logarithms to exponentials. The base b becomes the base of the exponential. The y, which for now appears on the other side of the equation, if we think of it that way, becomes the exponent, and the x that's in the parentheses, the item that we're taking the log of, becomes the equal to portion for the conversion. So when you're converting from log form to exponential form, b is your base, y is your exponent, and x is what your exponential expression is set equal to. Note also that your domain is all positive real numbers, and the range is all real numbers. So in other words, the x has to be positive, and the y in the log, or in the exponential expression that we're going to have, is always going to be all real numbers. We're going to restrict our discussions of logs to two basic types, one the common log and the other the natural log. So let's first take a look at the common log. The logarithm with base 10, logarithm with 10 as its base in other words, is called the common logarithm, what I sometimes refer to as the log log. When the base is not indicated, and we write as log of b, so without a little subscript, we understand this to be the common log. So how do we interpret log of b? Well, let's take a look at an expression written in the form b equals 10 to the a. If I go back to my definition and I convert, what this actually could be converted into is a log statement, which says the log of b is equal to the exponent of 10 that would yield b. And so what's going to happen is, when I think about this, the b is always the exponent on 10 that's going to produce that b. Let's take a look at a couple of examples. First of all, let's look at the log of 100. Well, the log of 100 is 2, because 2 is the exponent on 10 that yields 100. So when I look at the log of 100 statement, what I know is if I'm thinking in terms of exponents, which is really the easier way to think, I want to say to myself, okay, the log of 100 is going to be the number that would be the exponent on 10 that gives me 100. How do I get 100 as a power of 10? And I get it by doing 10 squared. Part B, log of 0.1. So if I wanted to compute that, I'd say, what exponent on 10 do I need to create, or do I need to have, in order to get 1/10? And the exponent on 10 that would give me 1/10 is the exponent of -1, right? 10 to the -1 is 1/10. So the log of 0.1 is -1. So what I did below here, just briefly, is I made a table, and what I did was I used, in the A row are all the exponents on 10, and on the B row are the corresponding powers of 10. So what this table actually would tell me is 10 to the 0 is 1, 10 to the first is 10, 10 to the second is 100, 10 to the third would be 1,000, 10 to the -1 is 1/10, 10 to the -2 is 0.01, 10 to the -3 is 0.001. Or I can think of it in reverse. The log of 1 is 0, the log of 10 is 1, the log of 100 is 2, the log of 1,000 is 3, the log of 0.1 is -1, the log of 0.01 is -2, the log of 0.001 is -3. Some of you may remember from doing logs before that if you want to take the log base 10 of something that is a power of 10, there's a couple of quick ways to do it. One, if the number is not a decimal, if it's the 1, 10, 100, 1000, really the quick way to get the log of it is to just count the number of zeros. And if the number is the log of 0.1 or 0.01 or 0.001, something that is a power of 10 but is less than 1, it ends up being that the log of that is negative, and it's actually equivalent to the number of decimal places that we have. So you'll notice that works in this particular circumstance.